Today, in this video, we would like to discuss about radiography technique in X-ray imaging for code PHY380 scientific instrumentation and application.
Our group consists of 5 members, which are Nur Aina Safia binti Khairuddin, Nur Idina Shafika binti Norazmi, Nur Sakina binti Muhammad Hatta, Nur Farisha Alia binti Abdullah, and Siti Norafia binti Abdullah. For introduction, the fundamental processes in medical diagnostics that allow for the observation of internal body structures are called radiographic techniques in X-ray imaging. From tumors and other abnormalities to infections and fractures, this imaging modality is essential for the detection and diagnosis of a wide range of disorders. Using electromagnetic radiation to make images of tissues, bones, and organs is the fundamental idea behind X-ray imaging. X-rays are a form of high-energy electromagnetic radiation that can penetrate the body. When X-rays pass through the body, they are absorbed by different tissues at varying degrees based on tissue density. Bones, being dense, absorb more X-rays and appear white on the radiograph. In contrast, softer tissues absorb fewer X-rays and appear in shades of grey, while air-filled spaces appear black.
So now, I'm going to explain to you guys the scientific instrumentation and application concept in X-ray imaging. Here are the scientific instrumentation of X-ray imaging. First, X-ray tube, where it has cathode, the negatively charged electrode that emits electron when heated. Second, anode, the positively charged electrode usually made of tungsten that electrostride, producing X-ray. Third, vacuum envelope, in case the cathode and anode to maintain a vacuum allowing electron to travel without interference. Fourth, focusing cork, shape the electron beam to ensure it hits a small target area on the anode, producing a focused X-ray beam. Lastly is cooling system, either oil or water cooler to dissipate the heat generated during the X-ray production. Second is high voltage power supply. It has transformer, step up the voltage from standard power supply to high voltage required for X-ray production, typically 30 to 150 kV. Second, rectifier, convert AC to DC to provide a consistent voltage to X-ray tube. Third, control console, allow the operator to adjust voltage, current, and exposure time. Third is collimator. It has adjustable aperture, limit the size and the shape of the X-ray beam, reducing patient exposure and improving image quality. Second, light field, project a visible light field that match the X-ray field to help position the patient correctly. Next is X-ray detector, has screen system, traditional method using photographic film and intensify screen to capture the image. Second is computed radiography, use a photostimulable phosphor plate to capture the image, which is then scanned and digitized. Next is direct digital radiography, has two, which is flat panel detector and charge coupled device. Lastly is image intensifier, used in fluoroscopy to convert X-ray into visible image. It is then captured by a camera. Next is image processing and display, has digital process unit, computer equipped with specialized software for processing, enhancing, and storing digital image. Second, monitor, high resolution screen for viewing and analyze the image. Third, PACS, Picture Archiving and Communication System, network system for storing, retrieving, managing, and sharing digital image. Next is radiation shielding and protection. First is lead apron and shield, protect patient and healthcare worker from unnecessary radiation exposure. Next, lead line rooms. X-ray rooms are often lined with lead to prevent radiation from escaping. Lastly, dosimeter, device worn by radiologists and technicians to measure the exposure to radiation over time. Next is specialized equipment. Firstly, fluoroscopy unit provide real-time imaging for guiding procedure using an image intensifier and monitor system. Secondly, mammography unit, specialized X-ray equipment designed for breast imaging, often featuring compression pedal and lower energy X-ray. Thirdly, scanner use a rotating X-ray source and detector array to create cross-section image of the body, which are then reconstructed into 3D image. Lastly, supporting infrastructure. First, patient positioning system, tables and support that help position the patient correctly relative to the X-ray source and detector. Next, automatic exposure control (AEC), sensor that measure the amount of X-ray radiation passing through the patient and adjust the exposure automatically to achieve optimal image quality. X-ray imaging is widely used across various fields due to its ability to provide detailed image of internal structure. Here are primary application concepts of X-ray imaging. First is medical diagnostic, which is fracture, identify and assessing bone fracture. Second is industrial application, material integrity, inspect weld casting and structural components for internal defect without damaging the material. Third is scientific research, structure determination, determining the atomic and molecular structure of crystal by analyzing the diffraction pattern of X-ray passing through them. Next is veterinary medicine, animal diagnostic. Similar to human medicine, X-ray are used to diagnose fracture, tumor, and infection in animals. Lastly, forensic science, evidence analysis examining internal structure of evidence such as bullet or bone fragment to assist in criminal investigation. X-ray imaging applications span a wide range of fields, leveraging the technology ability to non-invasively visualize internal structure. Advanced in imaging technique and digital processing continue to explain the utility and effectiveness of X-ray imaging in various applications.
I will continue about the detailed exploration about radiographic technique in X-ray imaging. So first one is the equipment and technical setting. For X-ray machine, modern X-ray machines consist of an X-ray tube that generates the radiation and a detector to capture the image. And for the technique factors, the adjustments such as kVp, kilovoltage peak, and MAS, milliampere seconds, are set based on the part being imaged, patient size, and desired image quality. These factors influence image contrast and exposure. The second detailed exploration is image quality and radiation protection. So for image quality aim for optimal resolution and contrast to visualize anatomical structures clearly. This requires balancing factors like exposure times and patient positioning. For radiation protection, use slit apron, thyroid shields, and other protective measures for both patients and operators to minimize the unnecessary radiation exposure. And the last one is the advancement and future directions. For technology advance, developments like computed radiography, digital radiography, and cone beam CT continue to improve imaging capabilities and patient outcomes. For integration with other modalities, for X-ray imaging is often integrated with other imaging modalities, for example, MRI and CT scan, to provide comprehensive diagnostic information.
Next is example of real-world implementation. First, X-ray radiography. X-ray radiography is to detect bone fracture, certain tumors and other abnormal masses, pneumonia and some type of injuries. Second, mammography. Mammography is radiography of the breast that is used for cancer detection and diagnosis. Third, compute tomography, or we all know as CT scan. CT scan is a sequence of cross-sectional image by combining computer processes and conventional X-ray techniques. 4. Fluoroscopy. Fluoroscopy is fluorescence slit to diagnostic procedure or to get real-time image of bodily activity. Lastly, we have airport security to scan baggage to check dangerous items like drugs or knife.
I'm going to talk about the potential, benefit, and challenges for radiographic technique in X-ray imaging. There's few potential for radiographic technique in X-ray imaging. The first one is it has potential in medical diagnosis. X-ray are essentially in diagnosing fracture, detecting tumors, and assessing condition within the body non-invasively. The second one, it has potential in industrial application. X-ray are used for inspecting materials in manufacturing, detecting flaws in welding, and etc. Benefits of radiographic technique in X-ray imaging. The first one is minimal radiation exposure. It has less exposure than other machines such as MRI. The second one is quick to perform. X-ray imaging is relatively speed and convenience, making it suitable for emergency situations where rapid diagnosis is crucial. The third benefit is it cost-effective. X-ray equipment is widely available and less costly compared to other imaging modalities such as MRI and CT scan. So, we already talked about the potential and benefit for radiographic technique in X-ray imaging. Therefore, let's talk about the challenges. The first challenges for radiographic technique in X-ray imaging is it has a low quality image. Achieving optimal image quality can be challenging, especially in obese patients or those with metallic implants, which can obscure and distort image. Interpretation of complex image requires specialist training to avoid diagnostic errors. The second challenge is it must have a technologist training that has a proper training and adherence to protocol. It is crucial for obtaining accurate image and reducing errors. This is because balancing the need for high-quality image with minimizing radiation exposure can be quite challenging. Therefore, it really requires skill and experience.
Next is a future development in X-ray imaging. First, high-resolution imaging. This process could enable more detailed visualization of internal structure, possibly at the cellular or molecular level, significantly enhancing early disease detection and diagnosis. Second, reduce radiation exposure. The primary focus is reducing patient radiation exposure during X-ray procedure. Improvement in the detector technology and image processing algorithms are anticipated to create more efficient systems that need less radiation to produce high-quality image. Third, 3D imaging and holography. These technologies could offer three-dimensional views of internal structure without requiring invasive procedure, providing a more comprehensive diagnostic tool. Lastly, portable and affordable X-ray device. The creation of smaller, more portable and cost-effective X-ray device could increase accessibility, particularly in remote or under-resourced areas. This would enable broader use in various settings, from small clinics to disaster zones.
In conclusion, for medical industry, radiographic techniques for X-ray imaging are essential because they offer priceless insights into the insect structure of the body. These methods make it easier to diagnose and treat a broad range of illnesses, from straightforward fractures to complicated disorders. Healthcare professionals can maximize the use of X-ray imaging to obtain clear, diagnostic, quality images while avoiding radiation exposure by being aware of the basic concepts, elements, and safety considerations.